Hello again. This video we're going to talk about using the closure properties for regular languages to simplify our proofs that languages are not regular. So what we do is we apply a closure property to get ourselves some new statement and end up using the pumping theorem on a different language that's actually simpler to use the pumping theorem on, while still proving our original language was not regular. So obviously you'll need to remember the pumping theorem for regular languages, but not quite as much as you did for the previous video. The thing that you will really need to remember for this video are what the closure properties for the regular languages are. So what set of operations that we can do to languages where all of the input languages are regular will always result in a regular language. So to recap, we know that the regular languages are closed under union, they're closed under negation, they're closed under intersection, and they're closed under set difference, which I'll represent with a minus sign. The negation and intersection will be the two that we'll use most here, but if you're not really familiar, if you don't really understand quite what I mean when I say the regular languages are closed under these operations, then you'll need to go back and look at some previous material because we'll be using these concepts heavily within this video. So just like in the last video, we'll talk about two examples, each of which will show a slightly different way of using the closure properties for regular languages to make our proofs that languages are not regular easier for us to do. So basically we try to simplify the difficulty of the resulting pumping theorem by using closure properties in a clever way. So the first language we'll look at is made up of A's followed by B's followed by C's, and there are 0 or more of each of these. And that's what this symbol means here. If the number of A's is 1, so if we have 1A, then the number of B's must equal the number of C's. The second language that we'll look at is just A's followed by B's, again, so that there are 0 or more of them, and that the number of A's is not equal to the number of B's. Now, we've already looked at a language where the number of A's is equal to the number of B's. That's the language ANBN, which we've looked at a few times before. Sometimes we'll write it as capital A, capital B. So the question is this language where the number of A's is not equal to the number of B's easier for us to handle? And by that I mean, is it regular? What I would suggest you do is look at both of these languages and see whether you think they're regular. And if they're not regular, what I would suggest you do, well, you are correct, they're not regular. But once you've decided that to yourself, what I would suggest you do is start thinking about how you would do the pumping lemma and figure out if you think that would be fairly complex. Now the answer is yes, it would be fairly complex, and we're not going to go through the actual pumping theorem for these because I don't see a lot of value in forcing you through a complicated pumping theorem proof. But what we're going to do is use some closure properties to make things simpler. So the first closure property tip or technique is to intersect your language with some regex so that you can add some extra constraints on the language. So if this is our language L, we think about the language L intersected with A, B star, C star. Now, we know that the A, B star, C star is a regular language because we've just represented it using a regular expression. And we know that the regular languages are closed under intersection. So what that means is L being a regular language implies that this new L dash is a regular language. So if we make the assumption that L is regular, then we can do this and we get an L dash, sorry, I should have put the dash, we get an L dash that is regular. If we can then prove that L dash is not regular, then by contradiction we've just proven that our original assumption was false and that L is not regular. So that's how we work through with the closure properties. We use the closure properties as a way of building up a proof by contradiction, and we get down to a final language which we end up proving is not regular using the pumping theorem, and then we prove by contradiction. Now there's also other ways to use the closure properties. We can actually use the closure properties to prove that languages are regular, but that's simpler, so we cover that in the lectures. This concept's a little bit more difficult. So let's look at that language L dash. What is the intersection of our language with all of the strings that fit this regex look like? Well, that regex has only one A. So the resulting language is simply, so L dash is simply A, B, J, C, K, such that obviously J and K are greater than or equal to 0 still, and J equals K. So we could actually simplify this by simply replacing J and K with the same letter, N. And then we can remove this separate constraint completely. Now, if you're looking at that language right now, you should think that that language is definitely not regular because it looks exactly like our A and B N case. And, in fact, if we were to do the pumping theorem, we can pump on this language here and end up with something that doesn't exist in the language L prime. And so by proving that L prime is not regular, we've proven by contradiction that L must not be regular. So we would pick a string such as A, B, K, C, K, and we would have only two possibilities for Y. Either Y contains an A or Y only contains B's. If Y contains an A, we pump out and it no longer fits this description here. If Y contains B's, then we pump in or out, it doesn't really matter, but we will no longer satisfy this condition here that the number of B's is equal to the number of C's. So the pumping theorem proof for this one is quite simple, slightly more complicated than the A and B N proof, but we can prove that L prime is not regular, and our assumption that L was regular led to the conclusion that L prime was regular, which is a contradiction, so we know that the original language L is not regular, and the key thing that we did was we intersected with a regex. Our second example, I'll just pause so you have a moment to think, but our second example is A's followed by B's, where they're not the same number of A's and B's. Now, the rule of thumb that we'll use here is the previous one, eventually, but also the idea of negating our language. So whenever we have a language that's regular, so if this is our language L, L being regular implies that the negation of L is regular because the regular languages are closed under negation. So what we'll do is we'll find the negation of this and we'll prove that that's not regular, which means that the original language can't have been regular either. Under the same principle that we were talking about before, we've built up a proof by contradiction. Yep. So, what is the negation of L? Well, most of you will immediately realise that it consists of the strings in A and Bn. Some of you will have also realised that that's not all of the strings that are in the negation of L. Now remember that when we talk about the negation of just one language, what we're really talking about is all of the strings that we can make in the alphabet of that language minus the language. So our universe in these cases is the alphabet clean. Now if we look at all of the strings that we can make using A's and B's, they're not all going to fit the A's being before B's rule. So as well as the strings that are in A and Bn, we will also have all of the strings where they're out of order. So I'm just going to say out of order. But the key thing about the strings that are out of order is that it's the negation of the regex A star, B star. So we've now got something where we're starting to see a little bit of a kernel of where we can go because we've got A and Bn in there. So it's quite possible that the negation of L is not regular. But we've got this pesky out of order extra set of strings that are being lumped in by a union. But we can look back at our previous rule of thumb, which was to intersect with a regex. So what I would suggest you do is just pause the video again and think what you would intersect the negation of L with to get just AN, BN. Now, what we've got in AN, BN is a set of strings that match A star, B star, and a set of strings that don't match A star, B star. So if I intersect the negation of L with A star, B star, the resulting language is our famous AN, BN. Now, we've already proven with the pumping theorem that that's not regular. So if you're allowed to assume a previous proof has existed, then we can stop right here. But for those of you who may want an extra bit of practice on the pumping theorem, you can go ahead and prove that one again using the pumping theorem. But the key takeaway from this is that we started with the language L, and we made the assumption that it was regular. And that has led to the conclusion that AN, BN is regular. Now that is a contradiction, which means that our original assumption was incorrect, which is our proof by contradiction. So in this, the key steps were negation, but also we ended up needing to use our previous rule of thumb, intersecting with a regex, in order to clear up some pesky little extra parts that were added. So, to sum up, we end up with in this video, two good rules of thumb that we can use to use the closure properties to help us make our pumping theorem proof simpler. So the first is we can use the fact that the regular languages are closed under intersection by intersecting the language that we care about with a regex so that we can enforce extra constraints. So a particular one, a good example might be the language where we've got the language where we've got W coming from A, B, clean, such that the number of A's in W is equal to the number of B's in W. Now that is a complicated pumping theorem proof to do, but it's easy if you intersect it with A star, B star, because the resulting language is AN, BN. The second rule of thumb that we've got is that we can often complement a language to make things easier by inverting the constraints on the language. So we saw that before. We had a language where the constraint was that two numbers are not equal. So we were able to negate that and get a constraint where the two numbers were equal. But we always have to be very careful to consider all of the possibilities, because often it won't just be a flipping of an equal sign or something like that. Often you'll end up including a bunch of other strings. So you may need to then apply an intersection with a regex to simplify things back down again.